It's me, Mr. Werger. Today's lesson is on hyperbolas. If that sounds familiar, we did hyperbolas back first semester when we were talking about rational functions. Real briefly, a rational function had x in the denominator. So just this basic 1 over x graph made a hyperbola. So there was a curve in quadrant 1 and there was another curve in quadrant 3. So those two curves together form what's called a hyperbola. Okay, so we're doing more with hyperbolas today, only the x and the y-axis are not going to be our asymptotes. We'll have different asymptotes depending on the equation. Okay, so components of a hyperbola. There's the center. And you'll see some similarities here between what we did with circles and ellipses and now what we're doing today with hyperbolas. So the center is HK, just like it was for circles and ellipses. If you have not viewed those lessons, if you were absent, you really should do that as soon as possible. Then there are two branches that make the hyperbola. So in the rectangular hyperbola, we saw the branches there and there. I'm going to draw the branches in quadrant 1, so maybe something like that. Okay, so those two curves together would make what's called a hyperbola. There are two vertices. So if you want to envision these as like individual parabolas for a minute, so think about a parabola and the vertex of a parabola. So if these were parabolas, the vertex might be there and there. It's very wide parabolas. Okay, so vertices, that's the plural of vertex. So there's two vertex points there. And the distance from the center is A. And you know what? I didn't put the center on here. So the center is halfway between the vertices. So the center of the hyperbola would be like right there. So then I'm saying this distance from the center out to one of the vertices, that distance is A. Okay. Okay, then there are two asymptotes with the rectangular hyperbola. Here it was the x and the y-axis. So here, what color should we use? The asymptotes do intersect at the center. So I would have an asymptote kind of going through like that. And another one kind of going through like that. So my asymptotes intersect at the center, and then these curves are kind of flaring out towards the asymptotes. Okay. So the asymptotes, we can say they intersect at the center. Okay, and then we have something called a transverse axis. A transverse axis basically connects the vertices. So my transverse axis would be like that right there. My green line is the transverse axis. And how long would the transverse axis be? Well, from the center out to one of the vertices is A. That's A plus A. The length would be 2 times A, right? Length equals 2 times A. Okay, and then there's something called the conjugate axis. The conjugate axis is perpendicular. We also remember the symbol for perpendicular, like an upside down T. So I have to write out that long word. So the conjugate axis is perpendicular to the transverse axis. And it goes through the center. And the length of the conjugate axis is 2 times B. So I'm not going to draw the conjugate axis right now. Once we get to an example with actual numbers, we'll do it there. But it's going to go, in this case, it's going to be vertical. It's going to go through the center there. Okay. So those are the components of a hyperbola. Then we have 2 equations. Those look very much like the equations for ellipses, right? What's the one difference? One difference is that it's subtraction, right? So being addition there, if this was addition, that would be an ellipse, but it's subtraction, so that makes it a hyperbola. Okay. So if you remember with hyperbolas, we said A was always greater than B. Okay, so that's not the case with hyperbolas. So A squared is always going to be with the first chunk of the equation, the positive part of it, I guess. So here A squared is with X. Here A squared is with Y. Here we have X squared minus Y squared. Here we have Y squared minus X squared. Both equations are still equal to 1. Okay, so when you've got X squared minus Y squared, then we've got a hyperbola similar to the one we just drew. Opening out to the sides. And this horizontal distance there, that's A. If we have Y squared minus X squared, now your hyperbola is going to open up and down, like that. So now your A value is going to be a vertical distance from the center up to one of the vertices there. Okay, so at some point before you draw your hyperbola, you want to look at your equation and see, okay, is it X squared minus Y squared, in which case it opens to the sides, or is it Y squared minus X squared, meaning it opens up and down. Okay. All right, so let's graph one of these with actual numbers. So I guess first thing to look at is seeing that it's Y squared minus X squared. Okay, so this is going to open up and down. Let's identify the center. And even though the Y part comes first, when you identify the center, the X coordinate is with X in the equation, and the Y coordinate is with Y. So the center would be -1 and 5. Okay. So -1, 5. There's our center. Okay, so then the number under the positive part here, that's a squared. That's a squared. So just like with ellipses, we took the square root, right? Just divide a. So a would be 5. Okay, and since this is opening up and down, I'm going to move a units in the vertical direction, up and down from the center. Okay, so from here I need to go 5 up and 5 down. So we're going to have to extend our y-axis here a little bit. 6, 7, 8, 9, 10. Okay, so there's one of the vertices. Down 5 puts me right back on the x-axis. So those are vertices. Okay. The b value, so b squared is 9. So b is 3. Okay, so now we can do this conjugate axis that I was talking about. So if I start at the center and go 3 in each direction, 1, 2, 3, 1, 2, 3. Okay, so this is your conjugate axis right there. I don't know if you really need to draw the conjugate axis. It's not like a super important thing. But if you were wondering what it was, that's what it is. And I guess if we want to draw in the transverse axis here too, just so we can kind of see it. So that's the transverse axis. Okay. So now what I'm going to do is like create a little box. This is pretty important. So let's see. From the vertices, I'm going to go out. So the axes kind of bisect our box. So if I start at my vertex point here and go out 3, and go out 3 the other way. Do the same thing with this vertex point, go 3 this way, and 3 this way. Okay, so I've created like this rectangle. Let's run this rectangle here. Okay, so I started at each of the vertices and then the b value 3. So I'll go 3. In this case to the left, 3 to the right, down here, 3 to the left, 3 to the right. Okay, so I've got this rectangle. So my asymptotes are going to be the diagonals of this rectangle. Hope you can see yellow on the video there. So I'm drawing diagonals through that rectangle, which would also go through the center. We said the asymptotes intersect at the center. So now I can kind of draw in my hyperbola. Let's go blue. So I would start at each of my vertices and then draw a curve that kind of flares out towards the asymptotes. So you kind of need the asymptotes to draw the hyperbola. Blue curves, that's your actual hyperbola. Okay. Okay. this with circles and ellipses. Rewriting an equation in standard form. So standard form looks like, one of these. Where we've got x minus h squared, y minus k squared, over a squared, b squared equals 1. Okay. And we're going to follow the same steps we did with ellipses. Follow the same steps you did with ellipses. Follow same steps we used for ellipses. Okay, so I'm not going to rewrite all 5 steps. Should be right there in your note packets. So step 1 was to rearrange our terms. So our x terms were together and our y terms were together. Okay, so I've got y squared minus 4y. Since the y squared is positive and the x squared has a negative coefficient, I'm putting the y squared first. So remember, it's subtraction. Okay, and then we've got minus 4x squared minus 24x. And then if there's a constant, we want to move that to the other side of the equation. So that would become positive 28. Okay, that's step 1. Step 2 involves factoring. We want to factor out the coefficients of x squared and y squared. So I do not need to do anything with y squared because the coefficient there is 1. So I've just got y squared minus 4y. I'll leave a space there. The coefficient of x squared is negative 4. So I'm going to factor out negative 4. Hyperbolas will have more negative signs going on. So be careful with those. It's easy to inadvertently leave out a negative somewhere, and then that messes up everything. So a negative divided by a negative here, that's going to become positive x squared there. Negative 24 divided by negative 4, that becomes plus 6x. Leave a space, equals 28. Okay, step 3, take half of the b value and square it. So half of negative 4 is negative 2. Negative 2 squared is 4. I added 4 here, so I need to add 4 here. Then we want to look at the new b value after we do the factoring. So half of 6 is 3, 3 squared is 9. Okay. And then just like ellipses, we need to multiply this number by whatever we factored out. So here I'm multiplying negative 4 times 9, which is negative 36. So on the other side of the equation here, negative 36. With ellipses, we said this number would always be positive. Not the case with hyperbolas. So if you get a negative number here, that's okay. Then we simplify. So we can write this in factored form. Y minus 2 squared minus 4 times half of b's, x plus 3 squared. 32 minus 36 would be negative 4. following this. Then the last step, we want our equation to equal 1. So we divide by whatever we ended up with here. So I'm going to divide by -4. Okay, and then kind of pay close attention here to what happens. So looking at the x part, I've got -4 divided by -4. So that becomes +1. Okay, so these two terms are kind of going to switch position because we're dividing by a negative here. So this part's going to become positive. So I want to write that first. X plus 3 squared. And I guess if you want to have a denominator there with your a squared value, a squared is going to be 1. And the y part, we're dividing by a negative. So I'm just going to move that negative up to make it subtraction. We should have subtraction for hyperbola. Y minus 2 squared over 4 equals 1. Okay, so there's our equation in standard form. And then we're supposed to sketch a graph. Here. So identify your center, looking at the h and the k values. -3, 2. -3, 2. Okay, we have x squared minus y squared. So that tells us that this hyperbola opens to the sides. A squared is 1. Square root, so a is also 1. So from the center, I go 1 to the left and 1 to the right. There's my vertices. B squared is 4. And remember we said a squared is not necessarily bigger than b squared. So here b squared is bigger. That's okay. So b is 2. Okay, so then from the vertices, I would go up 2 and down 2. Up 2, down 2. Up 2, down 2, from each of the vertices. Okay, so here's this rectangle. And then draw in the diagonals of that rectangle. Those are your asymptotes. Okay, and then from the vertices, draw your hyperbola, going out that way. All right. So your homework is worksheet 7. On the cover sheet, it also says worksheet 6, which is a review of logarithms. We're going to save that till next week. So you only need to do worksheet 7. And on number 2, you do not need to graph number 2. You do have to go through this process and rewrite the equation in standard form, but the a and b values are very small. I think some of them come out to be fractions. And unless we change the scale on our graph, which I guess we could conceivably do, but I think we'll just forego the graph on number 2. Okay? Okay. So please, hopefully you've watched this video and get the homework done prior to next class. Hope you're having a good week. And I guess I'll see you whenever I see you. Have a good day.